Hello students. In the previous lecture of kinematics of rigid bodies, we had covered rotation at length and we had also covered problems of general plane motion type 1. What was the type 1? Single bar in GPM. We covered 4 problems of single bar in GPM. Now we are moving to type 2. What is type 2 problems? 2 bars mechanism with one in rotation and other in GPM. In this mechanism, you come across the 2 bars, 2 rods or 2 beams which are connected together by means of internal hinge. At the end, one of the bars is connected to external hinge. The property of the external hinge is that it allows the bar to only rotate. So we remember it like this in 2 bar mechanism. One bar will be in rotation, other will be in GPM. Which bar will be in rotation? The bar which is connected to external hinge, right? The bar which is not connected to external hinge will be in GPM. This way we will identify which bar is in rotation and which is in GPM. All right, we will remember that the external hinge, if any body, any blink, any bar is connected to external hinge, it allows the bar to rotate about the hinge. The property of the hinge is that it allows the body to rotate about it. Now, to understand the other concept, you have to understand this diagram. Look at this diagram. In this diagram, you have the bar OA, which is hinged at O. All right. So once you connect this bar to hinge O at O, the hinge at O will allow only this bar to rotate about O. So suppose we want to mark the velocity of point A, B, or C. Velocity is always along the tangent. Tangent is perpendicular to normal. Suppose this bar is rotating in clockwise direction with angular velocity omega. So suppose we talk about point A. So point A, if you ask you to mark the normal is directed towards center of curvature. So this is normal is the axis of this bar, which is a dotted line. It is passing through O. This is normal direction. Well, as it is turning in clockwise direction, velocity of point A will be perpendicular to normal. As it is turning in clockwise direction, velocity of point A will be perpendicular to OA and it will be down this way. So VA will be perpendicular to OA. Similarly, velocity of point B will also be perpendicular to OB. Similarly, velocity of point C will be perpendicular to VC because velocity is always tangential. But when we are solving the problems, we do not mark tangent and normal, right? We will simply remember that velocity of a point on the bar in rotation will always be perpendicular to the bar. What will remember that? Velocity of any point on the bar in rotation will always be perpendicular to the bar. Reason for developing this concept is that because the bar itself will be normal direction and velocity will be perpendicular to the bar. As you can, with this explanation, I think it should be clear that velocity of any point on the bar in rotation will always be perpendicular to the bar because bar itself works as a normal direction. You can see in this case, velocity of point A, B, and C are perpendicular to bar OA. With this understanding, we are ready to start with the problems of type 2. Now, as you can see the title, you should remember that here you come across a 2 bars mechanism with one in rotation, other is in GPM. First problem of this type. In the figure, caller C slides in a horizontal on a horizontal rod in the position shown. Rod AB is horizontal, has angular velocity of 0.6 radian per second clockwise. Determine angular velocity of BC and velocity of caller C. Now, if you look at this diagram, here it is 2 bars mechanism. What are the 2 bars? AB and BC. B is hinged, internal hinge. B is internal hinge. Bar AB and bar BC are connected at B by internal. All right. Then, since bar AB is connected to external hinge at A, we'll understand that bar AB is in rotation. We understand that bar AB is in rotation and bar BC is in general plane motion. Now, we draw the line diagram. As we discussed, we'll draw the line diagram. So I draw AB, which is horizontal. It is rotating at the instant, at this instant at 0.6 radian per second clockwise. All right. Velocity of point C will be horizontal. Why velocity of point C will be horizontal? Since it is connected to a collar which is sliding on a horizontal rod. Velocity of point C on the bar BC will be horizontal. Why it will be horizontal? Since it is connected to a collar which slides on the horizontal rod. So velocity of point C can be to the right or can be to the left, but it has to be horizontal. velocity of point C has to be horizontal, either towards right or it is towards left. We assume the velocity of point C towards right. Now, first we'll consider motion of bar AB. Now, if you look at motion of bar AB, it is rotating in clockwise direction. So velocity of point B will be perpendicular to AB. Velocity of point point B will be perpendicular to AB. It will be vertically down. Why it is vertically down? Since bar AB is horizontal, velocity of point B will be perpendicular to AB. Since it is rotating in clockwise direction about A, velocity of point B will be vertically down, perpendicular to AB but down. Now, as omega AB is given to you, velocity of point B can be right. Velocity of point B is omega AB into AB distance. Omega AB is 0.6, AB distance is 140. So this comes out to be 84 mm per second. Now, velocity of point C, as we understood, it has to be horizontal, either to the right or to the left. Suppose we have assumed it to the right. Now, we can come to the motion of part BC, bar BC, which is in general plane motion. See, AB was in rotation, so rotation means what? It rotates about fixed axis. It is rotating about hinge A. Whereas for bar BC, we have to locate ICR. How we locate ICR? Now, direction of the velocity, the 2 points are known. They are known parallel. So you'll locate ICR by simply drawing perpendicular to VB and BC. Draw perpendicular to VB, draw perpendicular to BC. Right? Where they intersect, that becomes your ICR. Keep your pen or pencil at I. All right. Then look at the direction of VB. You'll understand that bar BC appears to rotate in clockwise direction. So omega BC will be VB upon VI. Omega BC will be VB upon VI. VB is already known to 84. BI distance is what? 240. So you get 0.35 radian per second clockwise. Then you want to find velocity of point C. Velocity of point C has to be perpendicular to CI. Right? Keep your pen or pencil at I. Look at VC. It is also giving clockwise rotation to the bar BC. If you keep pen or pencil at I, look at direction of VC, you will understand that VC is giving clockwise rotation to bar BC. That means assume direction of VC towards right is correct. So VC will be omega BC into CI distance. Omega BC, we got it 0.35. CI distance is understood to be 180 from the given diagram. So you get the VC as 63 mm per second towards right. This type is most important type out of the 6 types. We have already covered type 1 problems. Now type 2, I'll be discussing 4 problems as this type is very, very important. In my opinion, type 1 and type 2 are the most important. Type 3, type 4, type 5 are little less important. So we'll be discussing 2 problems of each type. In this type, I'll be discussing 4 problems. Although the steps are identical, but still to give you better exposure to the solved problems, so we'll discuss 4 problems. Let's discuss next problem. Rod AB has angular velocity of 2 radian per second counterclockwise. What do you mean by counterclockwise? Anti-clockwise, as shown. And C of the rod BC is free to move on a horizontal surface. Now again, students, what you need to understand, this and C is bound to move on a horizontal surface. That means velocity of point C is horizontal. Velocity of point C is horizontal. Is that clear to everybody? Now, determine number 1, angular velocity of rod, angular velocity of BC and velocity of C point. Slight printing error is there in the problem. What is that? At B, internal hinge is missing. At B, internal hinge is missing. There has to be internal hinge at B in the problem. So there are 2 bars in the mechanism, bar AB and bar BC, and 2 bars are connected together at B by internal hinge. So we'll understand bar AB is in rotation, bar BC is in general plane motion. Right? We start with we draw the line diagram. You can see that I've shown at A and A. This is a line diagram for bar AB. All right, it is omega AB is anti-clockwise 2 radian per second. This angle is 40 degree given to you. Length of the bar AB is 0.3 meter. So velocity of point B will be perpendicular to AB. Velocity of point B will be perpendicular to AB. Since it is rotating in anti-clockwise direction, velocity of point B will be perpendicular in this way. Right? We can find the velocity of point B on the bar AB. What is velocity of point B? Omega AB is given into AB. Omega AB is 2. Length of the bar AB is 0.3, so 0.6 meter per second. You marked it. This is internal hinge, so we have shown it with the dot. Now bar BC length is given 0.5. This angle is 40. Now students, if this is being turned in anti-clockwise direction, bar BC is in general plane motion. We understood that bar AB is in rotation since it is connected to external hinge at A. Bar BC is not connected to any external hinge. That means it is in general plane motion. All right. Now we have to locate ICR for bar BC. Velocity of point B is on bar BC is known to you. See, velocity of point B, we marked it based on motion of part AB, but it will work for part BC also. So on part BC now, when you are considering part BC, velocity of point B is known. All right. Velocity of point C will be horizontal. You assume it to the right or you assume it to the left. Anything you can assume it. So we have assumed it, say, to the right. Now to locate ICR for bar BC, you need to draw perpendicular to VB and VC. We draw perpendicular to VB. We draw perpendicular to VC. Where they intersect, that becomes your ICR. Now students, this angle 40, this was 40 degree. So this angle will also be 40 degree. The two bars AB and BC are mutually perpendicular. You can see that this angle is 90 degree. All right. And this angle is given to you 40. So this angle will become 50. All right. So in short, triangle BCI is right angle triangle. Triangle BCI is right angle triangle. So in this triangle, if I take 10, 50, it will be BI upon 0.5. That is BC. So you get BI distance. And cos 50 is base upon hypotenuse. Base is BC, that is 0.5, upon hypotenuse is CI. So you get CI. Now keep your pen or pencil at I. Look at the direction of VB. You'll understand that bar BC appears to rotate in anti-clockwise direction. So omega BC will be VB upon BI. Omega BC is VB upon BI. VB is 0.6, which we got it from here. And BI distance, we got it 0.6. So it comes 1 radian per second anti-clockwise. Then you want to find velocity of point C. Keep your pen or pencil at I. Look at the direction of VC, which was assumed one. We assumed it to the right. But if you keep pen or pencil at I, direction of VC is such that it is giving same anti-clockwise rotation. So that means direction of VC is correct. Assume direction of VC is correct. What is VC? Omega BC into CI. Omega BC is 1 and CI length, we got it 0.778. So velocity of point C is 0.778 meter per second towards all right. We take the next problem of the same type. In a crank connecting rod mechanism, lengths of crank and connecting rod are 300 mm and 1200 mm respectively. That means this is crank, this is of 300 mm and this is 1200. Crank is rotating at 180 rpm. Find the velocity of piston when crank is at an angle of 45 degree with the horizontal, assuming that crank is rotating in clockwise direction. Crank is rotating in clockwise direction. We have to look into the problem as it is a two bars mechanism. What are the two bars? AB and BC. They are connected by internal hinge at B. Bar AB is connected to external hinge, so it will be in rotation. Bar AB will be in rotation and bar BC, since not connected to external hinge, will be in general plane motion. So we draw the line diagram. I have shown hinge A, we have drawn AB, right, which is of length 300. We have shown the other bar of length BC. A and C are at the same level, so you can see that this angle is given to us 45 degree. All right. Now here, to find the distance in this problem, you can use either sine rule in this. You can use sine rule in this triangle. 300 upon sine theta, 1200 upon sine 45. Then also theta angle can be arrived. But here I have found angle theta. We're using different geometry. Now first we'll understand, since AB is in rotation, omega AB is given to you clockwise. So we first convert it into radian per second. Omega AB is 180 rpm. 180 into 2 pi by 60, 18.85 radian per second clockwise. Since omega AB is clockwise and AB is in rotation, velocity of point B will be like this, perpendicular to AB. Right? What will be VB? Omega AB into distance AB. Omega AB is 18.85 and AB length is 300, that is 56.55 mm per second. Now, here to find angle theta, first I have considered this right angle triangle, triangle ABD. In triangle ABD, what will be distance BD? 300 sine 45. Then you come to triangle BCD. In triangle BCD, sine theta will be BD upon BC. BD is, we got it, 212.132 upon 1200. So that gets you theta 10.1. The other way of getting it was, could have been obtained in triangle ABC. You could have used sine rule, 1200 upon sine 45 equal to 300 upon sine theta. So that way also theta can be tried. All right. Now, again, we understand that rod BC is connected to a piston at C. And this piston, can you see that it is made to move in a horizontal track? Piston at C is made to move in a horizontal track. That shows that velocity of point C on the bar BC will be horizontal. Now, you have the choice to assume it either towards right or or towards left. So we have assumed it towards right. You already got velocity of point B on bar BC. You have marked the velocity of point C. You assume the velocity of point C, which you can assume it to the right or to the left, but you need to take it horizontal only. Draw perpendicular to VB and you draw perpendicular to VC. Where they intersect, that becomes ICR for bar BC. Students, now this angle theta we already knew, 10.18. Alpha will be 90 minus theta. We got it, 79.8. This angle is, since this angle is 45, this is 90, so this angle is 45. So in triangle BCI, beta angle will be what? 180 minus 45 minus alpha. You get it, beta. Then in triangle BCI, we can apply sine rule, 1200 upon sine 45, BI upon sine alpha, and CI upon sine beta. So all these values have been substituted. We get BI or IB and IC. Now you go to the motion of part BC now. Keep your pen or pencil at I. Look at direction of BB because this is definitely correct. Looking at direction of BB, you understand bar BC appears to rotate in anti-clockwise direction. Omega BC is VB upon BI. VB is 5655 mm per second. That is what we got it. And IB distance, we got it as 1670.34. So that gets you omega BC 3.855 anti-clockwise. All right. Now you want to find velocity of point C. Again, keep your pencil at I. Look at assumed direction of BC. What kind of the rotation it is giving to the bar BC? Anti-clockwise. That means assumed direction of BC is correct. Suppose you had assumed BC to the left. All right. So there will not be any change in the geometrical construction and the steps. Only thing is you'll realize that assumed direction of BC, which was assumed to the left, is wrong. You need to correct it and make it to the right. Then only this direction of velocity of point C will give you anti-clockwise rotation about I. Anyway, right now our assumed direction of VC is correct. So VC is omega BC into CI. What it is? VC is omega BC into CI or IC. Omega BC is 3.3855 into IC. IC is what? 1393.2. You get VC as 4716.7 mm per second or 4.717 meter per second, and it is to the right, horizontally towards right. We take one more problem, students, on the same type, as the type is very important. Problem number 4. At the piston shown in the figure, crank AB has angular velocity of 3 radian per second clockwise. Find the velocity of slider C and point D at the instant shown. Now look into the diagram. Again, is the 2 bars mechanism. 2 bars are connected together by internal hinge at B. Bar AB is in rotation. Why bar AB is in rotation? Since it is connected to external hinge at A. Bar CD is in general plane motion since it is not connected to any external hinge. Now we draw the line diagram. We have shown the line diagram, bar AB, bar CD, hinged at B. Omega AB is 3 radian per second. Length AB is 300 mm. So if you consider motion of bar AB, then VB will be omega AB into distance AB. Omega AB is 3. This is 100 AB. So VB is 300 mm per second. All right. Now here, velocity of point C as for bar CD, and C is connected to a collar which is made to move in a horizontal track. Again, I repeat, bar CD is connected to a collar which is made to move in a horizontal track. So velocity of point C will be horizontal. It can be assumed to the right or it can be assumed to the left. We have assumed it to the right. So now for bar CD, you can look at ICR. How do you look at ICR? Draw perpendicular to VC and draw perpendicular to V. Where they intersect, that becomes ICR. In the problem, this length is given to as 100. This length is given to as 125. So you can find BI length. How you can find BI length? It's a right angle triangle. BI is equal to BC square minus CI square. As you can see that here in triangle BCA. So BC is 125 and CI is 100. So 125 square minus 100 square, square root of the whole, that comes 75. Now in the same triangle, we'll find theta angle also. How do you find angle theta? Sin theta is equal to opposite upon hypotenuse. 100 upon 125, theta is right. All right. Now we consider the motion of part CD. We consider the motion of bar CD. Keep your pen or pencil at I. Look at direction of VB. Look at direction of VB. The bar CD appears to rotate in anti-clockwise direction. Is it understood? Based on direction of VB, bar CD appears to rotate in anti-clockwise direction. So omega CD will be equal to VC upon CI. VB upon VI. Based on direction of VB, it appears to rotate in anti-clockwise direction. So omega CD is VB upon VI. VB is known to you as 300 mm per second. VI length is 75. So this is 4 radian per second anti-clockwise. To find the velocity of point C, now again keep your pen or pencil at I. Look at direction of VC. Does it give anti-clockwise rotation or not? Yes. So velocity of point C will be omega CD into CI. Omega CD is 4. CI length is 100. That is 400 mm per second. Now he's also asking you to find the velocity of point D. How do you get velocity of point D? The velocity of any point on the bar in GPM is obtained by joining that point with ICR. ये देखो point D को मैंने ICR से join कर दिया. Velocity of point D will be perpendicular to DI. Since DI perpendicular to DI. Now since bar CD is in GPM, right? Velocity of point D will be perpendicular to DI. And since omega CD is anti-clockwise, velocity of point D will be perpendicular to DI so as to give anti-clockwise rotation to bar CD. Now, velocity of point D will be omega CD into DI. So DI length is required, students. Now, in this triangle, BDI, BI length is 75, BD length is 125. Included angle between them is 180 minus theta, that is 126.87. So length DI is arrived at. Length DI is what? Square root of. Now we are applying cosine rule in this. 125 square plus 75 square minus 2 into 75 into 125 into cos of included angle 126.87. Length DI is arrived at. Now, since this bar, we have to find inclination of velocity D. So this bar, I'm assuming this length, the line, dotted line DI is making suppose angle alpha with horizontal. Velocity VD, normal to it, will make angle alpha with vertical. To find angle alpha, you can use sine rule in the same triangle BDI. How you apply? DI upon sine 126.87 is equal to 125 upon sine alpha. So that gets you alpha. All right. Now velocity of point D is omega CD into DI. Omega CD is 4. DI distance, we got it 180.28. That comes 721.11. And this velocity of point D will be at angle alpha with vertical. This dotted line is this is vertical. So this dotted line DI is making alpha with horizontal. Velocity of point D will make alpha with vertical. So we have shown it alpha with vertical. All right. So these were the 4 problems which we have discussed on type 2 problems of GPM, that is 2 bars mechanism with one in rotation and other in. We are ready to move to then type 3 sums. Please keep understanding the difference in various types of the problems, because in the examination, you have to identify first which type of the problem it is. Then accordingly, you need to solve. Now, 3 bars mechanism with 2 in rotation and 1 in general plane motion. As in type 1, we had single bar in GPM. In type 2, we had 2 bars mechanism with 1 bar in rotation and another in GPM. In this type, we'll have 3 bars mechanism or 3 rods mechanism or 3 beams mechanism, where 2 will be in rotation and 1 will be in G plane. The configuration of the mechanism is something like this. At the end, the 2 bars will be connected to the external hinges. So 2 end bars which are connected to external hinges will be in rotation. Like you can see that in the problem number 1, bar AB is in rotation since connected to external hinge. Bar CD will be in rotation since connected to external hinge at D, and middle bar BC will be in general plane motion in this type of the problems, because middle bar will not be connected to any external hinge. So let's read the problem. Right, in the position shown in the figure, bar AB has angular velocity of 3 radian per second anticlockwise. Determine the angular velocity of bar CD. Now students, we have understood that AB is in rotation since connected to external hinge at A. Bar CD is in rotation since connected to external hinge at D. Middle bar BC is in general plane motion. Now come to the motion of bar. You draw the line diagram showing 3 bars here, right? B and C, you should put a dot to indicate that these are interlinked. Velocity of point B will be perpendicular to AB. Since omega AB is anticlockwise, velocity of point B will be vertically up. Perpendicular to AB, but upward. Velocity of point B will be VB will be omega AB into length AB. Omega AB is 3 and length AB is 240. So you get velocity of point B as 720 mm per second. All right. Now we have to, from bar AB, you cannot go directly to bar CD. From bar AB, you have to go to bar BC. So first, you need to mark velocity of point C. As bar CD is rotation, velocity of point C will be perpendicular to bar CD. As AB is rotating in anti-clockwise direction, right? Bar C will tend to go up. That means it is bound to rotate about point D in clockwise direction. So velocity of point C will be perpendicular to CD and it will be up like this, perpendicular to CD, since omega CD is likely to be clockwise. Once you have marked VB and VC, draw perpendicular to VB, draw perpendicular to VC to locate ICR for bar BC. Now in bar BC, this length is, now just see that this angle will be 45. How come you understand this angle is 45? Just you see that this distance is given to you as 150. This is given to you as 150. That means this inclination of this bar CD is 45 degree with horizontal as well as with vertical, right? So I have marked this as 45. Bar BC is of length 350 mm. You can see that from here. Bar BC is of length 350 mm, right? This is 45 degrees, so this will also be 350. All right. Now keep your pen or pencil at I. Look at the velocity of point B. You'll understand that bar BC appears to rotate in clockwise direction. So omega BC will be VB upon BI. VB we understood it 720. BI length we understood 350. How come you understood? How you got it 350? Because the bar BC is of 350. This angle is 45. So orally we can understand BI length is also 350. So we got omega BC is 2.057 radian per second. It is clockwise. Now you want to find velocity of point C. Velocity of point C, direction of velocity of point C is correct since VC is giving clockwise rotation to bar BC with respect to ICR I. All right. Then velocity of point C, VC is equal to omega BC into CI. Right. Omega BC is 2.057 and CI length is going to be square root of, that is 350 square plus 350 square root of that, or directly I can say that this length is 350, BC is 350, so diagonal will be 350 root 2. So you get 1018.28 mm per second. Then you come to bar CD. Bar CD is in rotation. All right, it is rotating about a hinge D. Omega CD will be clockwise. So omega CD will be VC upon CD. For bar CD, velocity of point C, which you got it for bar BC, will work for bar CD also. So when you consider motion of bar CD, omega CD will be VC upon CD. VC is already known to you, that is 1018.28, and length CD will be 150 root 2. Why again 150 root 2? Because this is 150, this is 150, diagonal length will be 150 root 2. So omega CD is 4.8 radian per second clockwise. We'll solve one more problem. This type of problems are relatively simple because in 3 bars mechanism and 2 bars are in rotation and middle bar is in G. Now we'll take one more problem of type 3. If link CD is rotating at omega CD is 5 radian per second anti-clockwise, determine the angular velocity of link AB at the instant shown. Student, you can see that in this part, in this AB is in rotation since connected to external hinge at T. Bar CD is in rotation since connected to external hinge at T. Middle bar BC is in GPM, right? Middle bar BC is in general PM. 3 bars are connected at B and C by internal hinges. 3 bars are connected at B and C by internal hinges. Now we draw the line diagram AB, BC, and CD. Omega CD is 5 radian per second anti-clockwise. Length CD is 100 mm. Velocity of point C will be perpendicular to CD and it will be down like this. Velocity of point C is perpendicular to CD, all right, and it is down this way. Velocity of point C will be omega CD into length CD. So this is what we have arrived at. Bar CD. BC is omega CD into CD. Omega CD is 5, length CD is 100. So 500 mm per second. Now we understand that since bar AB is in rotation, velocity of point B will be perpendicular to AB. Now we can take it vertically down or vertically up. Now why I have decided to take vertically down? Because if you look at this mechanism, if CD is rotated in anti-clockwise direction, it is likely that bar B will tend to come down. It is likely that bar B, point B tends to come down. So we have assumed that AB is going to rotate in clockwise direction about point A. So if omega AB is assumed clockwise, VB will be perpendicular vertically down. So we are drawn. Now we draw perpendicular to VB, we draw perpendicular to BC, and ICR is located. All right. Now here, students, this angle is given 30. So this angle will be 60. All right. Then this angle is 45. This angle is 45 as alternate angle because it is a continuation of the same. All right. Now we got this angle 60, this angle 45. So this angle can be arrived at. How this angle will be arrived at? 180 minus 60 minus 45. So that comes 75. In triangle BCI, we can apply sine rule. How we apply? 200 upon sine 45, BI upon sine 75, and CI upon sine 60. You get IB and IC. All right. Then we come to the motion of bar BC. Keep your pen or pencil at I. Look at direction of BC. Bar BC appears to rotate in clockwise direction. Omega BC is VC upon CI. VC is 500. All right. CI length, we got it. CI or IC, 244.95. So omega BC is 2.041 radian per second clockwise. You want velocity of point B? Velocity of point B will be omega BC into BI. Right? IB 273.2. So VB is equal to omega BC into IB. VB is equal to omega BC into BI. Omega BC is 2.041 and IB distance is 273.2. So you get velocity of point B is 557.67 mm per second. And our assumed direction of VB down is correct. How come? Because with reference to, if you consider the motion of bar BC, by keeping your pen or pencil at I, if BC was giving clockwise rotation, even VB is also giving clockwise rotation. So direction of VB perpendicular to AB, what we assume vertically down, is correct. Now we come to the motion of part AB. Part AB or bar AB is in rotation. It is rotating about A. Omega AB is VB upon AB. VB upon AB. VB we got it 557.67 and length AB is 150. So 3.718 radian per second. So this way, students, we have discussed two problems on type 3, right? 3 bars mechanism, where 2 bars are in rotation and 1 is in general plane motion. Middle one normally and 2 bars are in rotation and middle one is general plane motion. Now we are ready to move to the next type, that is type 4. Type 4, circular body in GPM. When a cylinder or wheel rolls without slip, its point of contact with the plane is taken as ICR. When a cylinder or wheel rolls without slip, its point of contact with the plane is taken as ICR. What do you mean by no slip? No slip means what? Suppose your wheel has turned by 1 revolution, length or distance covered on the plane will be one full circumference, that is equal to 2 pi r. This type of problems are relatively simple since ICR is already known to us. Now let's take first problem of the type. A compound wheel rolls without slipping as shown in the figure. Velocity of center C is 1 meter per second. Find the velocity of points A, B, and D. Now, this is a compound wheel. This compound wheel, where do we come across, students? We come across compound wheel for railways, railway coaches, wagons, locomotives, all are provided with the compound wheel. Because in railways, the the driver of the train does not have any steering system. He does not have any steering system. All right. Then the movement of the train is governed by the alignment of the rail. So smaller part of the wheel rests on the rail. Bigger part of the wheel is projected beyond the rail level on the outer face, so that it is wheels keep the train locked on the rails. Now, but anyway, right now we need to understand that it's a compound wheel, a wheel having two sizes, smaller part and bigger part. The smaller part is resting on the rail, so point E will act as ICR. And he has given that is rolling without slip. It is rolling without slip, so point of contact of the wheel with the plane is E. That is point ICR. So we draw the line diagram little to the bigger scale. All right. Then point E is the wheel is in contact with the plane, that is ICR. Velocity of point C is given 1 meter per second. So omega angular velocity of this wheel is VC upon CI. VC is given to you as 1. IC distance of CI is 0.1. So omega is 10 radian per second clockwise. Now you want to find velocity of point A. So point A should be joined with ICR. We have joined it. Velocity of point A will be perpendicular to AI in such a way it gives clockwise rotation. Since omega is clockwise, so BA is perpendicular to AI towards right is correct. BA is equal to omega into AI. Omega is 10, AI length is 0.3. So that is 3 meter per second towards right. You want velocity of point B. B should be joined with ICR. Velocity of point B will be perpendicular to BI in such a way it gives clockwise direction. That means its direction towards left is correct. VB is omega into BI. Omega is 10, BI is 0.1. So that is 1 meter per second towards left. Now, you want to find velocity of point D. Point D should be joined with ICR. Since omega is clockwise, velocity of point D is perpendicular to DI. All right. Now, DI is making angle theta with vertical. BD will make theta with horizontal. Now, velocity of point D will be omega into DI. Omega is 10. Length DI is 0.2 square plus 0.1 square root of that. That is 2.236 meter per second. All right. Then you can find this angle theta. How will you find angle theta in triangle, right angle triangle CDI? Tan theta is equal to CD upon CI. CD is 0.2, CI is 0.1. So you get theta. So length DI, DI is making theta with vertical, BD will make theta with horizontal. That's what theta has been. All right. Now we take one more problem. We take one more problem of the time. A wheel of 2 meter diameter rolls without slipping on the flat surface. The center of the wheel is moving with a velocity of 4 meter per second towards right. Determine the angular velocity of the wheel and velocity of point P, Q, and R. He is asking you to find out the angular velocity of this wheel, and its diameter is 2 meter. That means its radius is 1 meter. Velocity of point center point is 4 meter per second towards right. So students, we draw the line diagram. We have shown the plane. Obviously, ICR is point of contact of the wheel with the plane, which we have marked it, since it is rolling without slip. Velocity of center point O is given 4 meter per second to the right. So that means whether if you keep your pen or pencil at I, direction of velocity of point O makes you to understand that wheel appears to rotate in clockwise direction. So omega is going to be velocity of point O, that is 4 upon OI. So 4 upon VO is velocity of point O is 4 and IO or OI distance is 1 meter. As diameter was 2 meter, radius is 1 meter. So this comes 4 radian per second. So angular velocity of this wheel is understood to be 4 radian per second. You want to find velocity of point Q. Point Q should be joined with ICR. Velocity of point Q will be perpendicular to QI in such a way that it gives clockwise rotation. So its direction towards right perpendicular to IQ is correct. VQ is omega into QI or IQ. Omega is 4, IQ is 2 meter, that is 8 meter per second towards right. Then you want to find velocity of point R. Point R should be joined with ICR. This line is making theta with vertical. Velocity of point R will be theta with horizontal. How will you get the velocity of point R? Omega into IR. Omega is 4, IR is diagonal distance 1 square plus 1 square square root of that, or 1 root 2 directly could have written. So 5.656 meter per second. As you can understand here, students, this is 1 meter, this is 1 meter. So theta is 45 degrees. So line IR is making theta with vertical. Velocity of point R will make theta with horizontal. This is what is marked. Theta is 1. Then you want velocity of point P. Point P should be joined with ICR. Velocity of point P will be perpendicular to PI in such a way that it gives clockwise rotation. Velocity of point P is perpendicular to PI in such a way that it gives clockwise rotation. So it is to the right. What we have shown is correct since omega is clockwise. Now in triangle IOP, right? This distance POP is known to me 0.6 meter. OI is known to me 1 meter. Included angle between the two is sides of the triangle is 120 degree, 90 plus 30. So using cosine rule, length PI can be obtained. Again, I repeat that, students, in triangle IOP, right? This the length OP is 0.6 meter. IO is 1 meter. Included angle is 120 degree, 90 plus 30. So length PI in the triangle using cosine rule can be obtained. So PI is square root of 1 square plus 0.6 square minus 2 into 1 into 0.6 into cos of 120. That comes 1.4. Now BP we can find it out, omega into PI, but angle also is required. So in the same triangle we apply. You can remember it like this. Mostly students, whenever you are applying cosine rule to find the distance in this chapter, you will have to apply sine rule to find the inclination of the velocity. So now again we take line PI is making alpha with vertical, BP will make alpha with horizontal. BP will make angle alpha with horizontal. So how will you get it? PI upon sine 120 and PO upon sine alpha. So this way we get it using sine rule. In triangle, same triangle IOP using sine rule. 1.4 is PO upon, sorry, PI. PI is 1.4 upon sine 120 and this is 0.6 upon sine alpha. So you got alpha. So velocity of point P is omega into PI. Omega was obtained as 4. PI length is 1.4. So you get the value of VP as 5.6 meter per second. And it makes angle alpha with horizontal as marked. Why? PI is making alpha with vertical, so VP will make angle alpha with horizontal. So these were the two problems what we have discussed on type 4. Now we are ready to move to type 5. Now let's understand what is the type. Two parts mechanism with both in general plane motion. You saw that, students, we understood from the discussion of 4 types. Any bar which is connected to external hinge will always be in rotation. All right. In this problem, the two parts, whether two bars or 2 parts, maybe 1 bar, 1 cylinder or 1 wheel, they are connected by internal hinge, but none of the part is connected to external hinge. So that's why both the parts will be in general plane motion. As in this mechanism, all right, there are 2 parts which are in general plane motion. So there will be 2 ICR will be located, for one for each part. So this type is considered to be slightly difficult. All right. So need to be little more attentive. All right. Now we understand problem number 1. In problem number 1, I'm reading it. A uniform cylinder C to which is pinned a rod AB at A with other end B moving along a vertical wall as shown in the figure. If and B of the rod is moving upward along the vertical wall at a speed of 3.3 meter per second, find the angular velocity of the cylinder, assuming the cylinder is rolling without slip. If the cylinder is rolling without slip, its point of contact with the plane is taken as ICR. The two parts, AB, bar AB and cylinder, both are in GPM. They are connected together at A by interhinge. None of the part is connected to external hinge, so both will be GPM. Now we have drawn the line. This is your cylinder. For cylinder, this point of contact with the plane is ICR, which we have called it as I. All right. Bar AB is also in general plane motion, right? Velocity of point B is given vertically up. 3.3 we have marked as bar and B or and B of bar AB is being pulled up. Cylinder which is connected to bar AB by interlinge at A is likely to rotate in clockwise direction. Likely to rotate in clockwise direction. So that's why velocity of point A will be perpendicular to AI1 and it will be to the right. It will be to the right. I repeat again, as and B of bar AB is pulled up, cylinder tends to rotate in clockwise direction. So velocity of point A based on motion of cylinder will be perpendicular to AI1. So it will be towards right since cylinder tends to rotate in clockwise direction. Now, as data given is on bar AB, that is velocity of point B is upward 3.3 meters per second. We will consider motion of bar AB first. In bar AB, right, this draw perpendicular to VB, draw perpendicular to VA. Where they intersect, that becomes your point I2. All right. Then keep your pen or pencil at I2. Look at the direction of VB. Omega AB, bar AB appears to rotate in anti-clockwise direction. So omega AB will be VB upon I2B. VB upon I2B or BI2. BI2 is 1.126. So that is 2.931 radian per second anti-clockwise. Now you get velocity of point A. Velocity of point A is correct since VA is also giving clockwise rotation to bar AB. VA is omega AB into AI2, right? Omega AB is 2.931. AI2 is 0.65. You get 1.905 meter per second. You got velocity of point A. Now we consider motion of cylinder, right? Motion of cylinder, angular velocity of cylinder, that is omega C, will be VA upon AI1. VA we got it as 1.905. AI1 is 0.6, diameter of the cylinder, and that gets you the angular velocity of the cylinder as 3.175 radian per second. So this is the problem of the type where two parts are in GPM. So we call this type as two parts mechanism with both in GPM. We take one more problem of this type, two parts mechanism with both in GPM. In the given mechanism, roller D is constrained in horizontal slot. What does it mean? For bar CD, velocity of point D will be horizontal. If he says that end D is connected to a roller which is made to move in a horizontal slot or which is constrained to move in a horizontal slot, that means velocity of point D is horizontal. It may be to the right or it may be to the left. That's it. There is no other option. Find velocity of D and angular velocity of rods for the given instant if VA is 5 meter per second vertically upward. Here is given there. Now you can observe it that in this two bar parts mechanism, there are two bars. One is bar AB, another is bar CD. Both the bars are in GPM since none of the part is connected to external. Both the parts are connected at C by internal hinge. Bar AB. As data given is on bar AB, we need to start with motion of bar AB. We draw the line diagram showing AB and CD. We draw the line diagram, right, with AB and CD. All right. And A is being pulled up with 5 meter per second. Now we consider the motion of bar AB. If and A is pulled up with certain velocity, and B is bound to move to the left. So velocity of point B will be towards left. Velocity of point B as it is sliding along the horizontal plane has to be horizontal. Now since and A is pulled up, velocity and B will tend to move to the left. So velocity of point B is horizontally towards left. Draw perpendicular to VB, draw perpendicular to VA. Point of intersection is called as ICR I1. This ICR I1 is for bar A. Keep your pen or pencil at I1. Look at direction of VA. Omega AB will be clockwise as bar AB appears to rotate in clockwise direction. Omega AB will be VA upon I1A. VA is 5, AI1 is 0.4. This is given in the, you get it, omega AB as 12.5 radian per second. After that, now, what about direction of VB? Is it correct? Yes. Keep your pencil or pen at I1. Look at direction of VB. Yes, it is giving clockwise rotation, so that means it's correct. But is he asking velocity of point B? No. So we don't need to find. Now you have to go to the bar CD. You can go to the bar CD only when velocity of point C is known to you, because point C is the connection. The two parts are connected by internal hinge at C. So first you have to find velocity of point C. Then only you can go to motion of part CD. Now, to find velocity of point C should be joined with ICR. Point C should be joined with ICR I1. Velocity of point C is perpendicular to I1C. Velocity of point C is perpendicular to I1C so as to give clockwise rotation. Velocity of point C is omega AB into I1C. Omega AB is 12.5. I1C is this length. This is 0.4 square plus 0.2 square root of that, 4.507 meter per second. Now you want to find now velocity of point D. That means you need to go to the motion of need to consider motion of part CD. For part CD, which is in general plane motion, velocity of point C is known to you. You should find angle what VC is making with horizontal. See, if I1C is making angle theta with vertical, VC perpendicular to I1C will make theta with horizontal. How we get in triangle I1CF? Tan theta will be equal to 0.2 upon 0.3. You get it theta as 33.6. Now, as the roller at D is constant to move in a horizontal slot, velocity of point D can be assumed to the right or to the left. It has to be horizontal. So you can assume it horizontally towards right or horizontal towards left. We assumed it towards right. Draw perpendicular to VC, draw perpendicular to VD. Where they intersect, that point is called as I2. Now, in triangle CI2E, in I2CE, right, you get tan theta. Tan theta is going to be C upon I2E. C is 0.4, you get it I2E as 0.6. Then in the same triangle, you write sin theta is opposite upon hypotenuse. Opposite is 0.4 upon hypotenuse is I2C. You get I2C as 0.721. Right? Then you get to go to the motion of bar C. Omega CD is VC upon I2C. You keep your pen or pencil at I2. Look at the direction of VC. Bar CD appears to rotate in clockwise direction. So omega CD will be VC upon I2C. VC is 4.507. I2C is 0.721. You got it 0.25 per second. As omega CD is clockwise, so velocity of point D, which we assume to the right, it is giving anti-clockwise rotation to bar CD, but that is wrong. So that means velocity of point D, you keep your pen or pencil at I2, look at the direction. See, we understood from the direction of velocity of point C that omega CD is clockwise. So if you look at the direction of VD, the bar CD will rotate in anti-clockwise. So this assumed direction is wrong. So this is not to the right. Our assumption is wrong. It has to be to the left. We understand that it's to the left. No need to make any correction in the diagram. You can make it or you don't make it. That's okay. We have written it to this part. Since omega CD is clockwise, VD will be towards left to give clockwise rotation of bar CD. Hence, assumed direction of VD was wrong. So it is not to the right, it's to the left. How you get VD? VD is omega CD into I2D. Omega CD is 6.25. I2D distance will be what? We got I2E as 0.6. DE is 0.4. So this is 0.2. You get this as 1.25 meter per second, and that is to the left. So this way we have discussed two problems of this type. Students, again I repeat that type 1 and 2 are most important types. Most of the time the problem comes from type 1 and type 2, but problems have been asked from all other types also. That's why from type 1 I discussed 4 problems in my lecture. Type 2 I have discussed 4 problems in my lecture. Type 3, type 4, type 5 are lesser important, so we have discussed two problems, although more problems are given in the book. Now we are ready to move to the next and the last type of general plane motion problems. Now, first we'll understand this type 6. Body in GPM with velocity of 2 points parallel. We understand the bodies in general plane motion. In all the first 5 types of the problems, you saw that anybody which was in general plane motion, direction, the velocity, the 2 points were given and they were known parallel. If they are known parallel, we locate ICR by simply drawing perpendiculars. But in this type, the velocity of the 2 points are given and they are parallel. If they are parallel, then the problem goes to the concept of you can say that second case of locating ICR. When the velocity of the 2 points are parallel, how do you locate ICR? We simply draw a line joining the extremities of the 2 velocity vectors. Where this line intersects with the line joining the 2 points, that becomes your ICR. Here, there is one very important point which should be remembered in this problem. As right in the beginning, I had told you that this problem's solution is combination of analytical and graphical. So that's why I told you in the beginning, you should take some precautions. What are the precautions? Draw a line diagram. Size of the diagram should not be too big or too small. You should draw the diagram near the center of the page so that no working should go out of the page. Also, we understood you have to draw the diagram as proportional as possible in terms of angle and distance. In this type, there is one additional care required, which I have listed here. In this type of the problems, length of the arrow representing the velocity should be proportional to its magnitude while drawing the line. So this is another additional precaution to be taken, and its importance I'll explain to you when we are solving this. I read this problem. Due to slipping, point A and B on the rim of the disk have the velocities as shown. Determine the velocities of the center point C and D at the instant. You are given with a wheel or a disk for which it is having slip. Due to slip, velocity of point A and B are given. Velocity of point A is 1.5 meter per second towards right. Velocity of B is 3 meter per second towards left. So this is in GPM. Velocity of 2 points A and B are given. They are known parallel. Velocity of point A is 1.5. Velocity of point B is 3. So when we draw the line diagram, first precaution what you have to take. You will draw the arrow representing velocity of point A, that is 1.5, approximately half of the arrow representing velocity B. Suppose arrow representing velocity of point B, VB is 3. We have shown it by suppose 3 centimeter. All right, this should be 1.5 centimeter. If arrow representing velocity of point B, you have shown it by 5 centimeter. So arrow representing velocity of point A should be shown as 2.5 centimeter. Then draw a line joining the extremities of the 2 velocity vectors. Where they intersect the line joining AB, that becomes your ICR. Now, importance of taking the length of the arrow proportional to its magnitude. Suppose you take arrow representing VA and arrow representing VB almost equal. So what may happen? Your ICR will pass through center or not, but that will become wrong. So that's what is you need to take the length of the arrow proportional to the magnitude of the velocity. Right. Now we have got ICR. What we have got it? ICR. Again, I repeat, we have drawn the arrow showing velocity B proportional to its magnitude. Right? We have drawn arrow showing velocity of point A proportional to its magnitude. I mean, arrow representing VB should be approximately double of arrow representing velocity B. Draw the line joining the extremities of the velocity vector. Where they intersect with the line joining AB is ICR. All right. Now, to locate the point I, we use similarity of triangles. What similarity of triangles? Diameter is 0.48. Radius will be 0.24. What similar triangles? 3 upon BI and 1.5 VA upon AI. AI we assumed it X. So this length will be 0.48 my diameter minus X. So VA upon X, VB upon 0.48 minus X. Right? VA is 1.5, VB is 3. On simplification, we understand X, that is AI, distance is 0.16 meter. Radius CA or AC or CB is 0.24 meter. Right? So the length CI will be 0.24 minus 0.16.08 meter. Now, students, you want velocity of point C. Point C should be joined with ICR I. Keep your pen or pencil at I. Look at VA direction of VA or VB. You will see that this disk appears to rotate in anti-clockwise direction. So omega of this disk will be VA upon AI or VB upon VI. So we have taken VA upon AI, right? VA is 1.5, AI is 0.16. So you get angular velocity of this disk 9.375 with ICR at I. All right. Now you want velocity of point C. Point C should be joined with ICR. Velocity of point C should be perpendicular to Ci in such a way that it gives anti-clockwise rotation. So it will be horizontally towards left, perpendicular to Ci. Velocity of point C will be omega into Ci. Omega is 0.375. IC or Ci is 0.24 minus 0.16, 0.08. All right. Now VC is omega into IC. Omega is 9.375 and IC or CI is 2.08. So that is 0.75 meter per second. So one matter is settled. Now you want velocity of point D. He's asked that. Point D should be joined with ICR. We have joined. Velocity of point D should be perpendicular to DI. Velocity of point D should be perpendicular to DI in such a way that it gives anti-clockwise rotation. Right? In triangle CID. In this triangle, length CD is known to me. What is that? Radius 0.24. We know CI, that is 0.08. This angle is 45. So this angle is 135. How you got 135? See, in this in triangle CID, right? This length is 0.24. This is 0.08. Included angle is 180 minus 45. This is 135. So you can use cosine rule to get the length ID. ID is equal to, using cosine rule, square root of 0.24 square plus 0.08 square minus 2 into 0.24 into 0.08 into cos of 135. That comes out to be 0.302. Then velocity of point D will be omega into ID. Omega is 9.375 into 0.302. That is 2.383 meter per second. And now we assume that DI is making theta with vertical. So VD will make theta with horizontal. To find the angle theta, what DI is making with vertical, you have to use again sine rule in the same triangle CID. Now, ID upon sine 135, CD upon sine theta. ID is already known to you, that is 0.302, right? CD length is radius, that is 0.24. You got theta as 34.1. So we have understood that if lines DI is or ID is making theta with vertical, VD perpendicular to it will make theta with horizontal. So this way we understand that VD is omega into ID. Omega is 9.375, ID is 0.302, 2.83 meter per second, and it is making angle theta with horizontal. All right, students. Again, I repeat certain precautions to be taken. Draw only line diagram in this chapter. Your diagram should not be too big or too small, right? Draw the diagram near the center of the page, because draw the diagram proportional as proportional as possible in terms of angle as well as distance. In this type, especially type 6, you have to take one more additional care or so. That is, what is length of the arrow representing the velocity in the beginning should be proportional to its magnitude, so that you get correct location of ICR. You have not to draw, not to redraw the diagram, right? So students, this was all about our third chapter in the book, that is Kinematics of Rigid Bodies. Chapter is quite important from the examination point of view. Chapter is little difficult, especially general plane motion part, right? I have covered all the 6 types of the problems, and I have discussed 4 problems on type 1, 4 problems on type 2, 2 problems on type 3, type 4, type 5, and I have taken only 1 problem on type 6, and it is relatively lesser important. Same problem only has been repeated 2-3 times. Well, students, my video lectures are based on a QR code. So all this I advise, request you all to share this QR code with your friends, right? Because sharing is caring, right? These video lectures are totally free. All right, you can share the QR code of my video lectures with your friend, so they will also have the access of the video lectures. They will also be benefited. All right, now you all, if you want to refer to the more problems, you want to see more solved problems, multiple choice questions, all right, or some practice problems, you can refer to my book, right? Book is available in the local bookstores as well as on Amazon with the free delivery and some discount on Amazon also. All right. Amazon link is given in the video description of every lecture. All right. Make sure that keep learning in the best possible way, even if the examination is online or offline. Make sure that If you gain the knowledge, it will always help you. All right. Thank you very much.